Euler set out to develop a solution not only for the specific example of the map of Königsberg, but for a general graph with any number of edges and vertices in any arrangement. In a similar way, the solution that we have to develop for a graph problem in an interview setting has to work on a general graph, not just on an individual example that might be given to us. Now, the first attempt to solve any problem would be a brute force approach. Euler says that we can exhaustively list all possible paths of a certain length and see how many of them satisfy the conditions of the problem. But because there would be too many paths to enumerate, Euler dismisses it as an impractical solution. Nevertheless, it's good to start with a brute force approach just to confirm that you have understood the problem correctly. If there's any misunderstanding about the statement of the problem, then it's better for that misunderstanding to be discovered early in the interview. You don't want to spend a lot of time coming up with an algorithm only to find that you misunderstood the problem. Some additional terminology. The degree of a vertex in an undirected graph like this is just the number of vertices that are adjacent to the given vertex. And that is nothing but the number of edges sticking out from the vertex. So the degree of every vertex in this graph here is shown as a number written on that vertex. So notice here, for example, that the degree of this vertex is 1 because there is one edge sticking out from this vertex. The degree of this vertex is a 3 because there are 3 edges sticking out from it. The degree of this isolated vertex is a 0 since there are no edges sticking out from it. And notice that there is a self loop that we have in this graph. This vertex has a degree of 5 because there are 5 edges sticking out from it, including this self loop. In general, the graphs that we will look at won't have self loops, and they also won't have multiple edges connecting the same pair of vertices like we had in the graph for the map of Königsberg. So if we have a graph where there are multiple edges between the same two vertices, or if we have self loops, then we call this kind of a representation as a multigraph. It's not a regular simple graph, it's a multigraph. Almost all the interview problems that you will have will be on regular simple graphs, not multigraphs. But in this case, it turns out that the solution to this problem would be the same even if we had a multigraph, so it doesn't really matter here.